Welcome to our video lecture on topic 6, kinetics. Our objectives for today, we're going to describe collision theory and kinetic molecular theory of gases. We're going to state the postulates of collision theory and describe the action of catalysts. We're going to outline factors that affect rates of reaction and how rates of reaction can be measured. We're going to outline and then practice the calculation of rates of reaction. We're going to wrap up with a look at Maxwell-Boltzmann distribution curves. Our essential understanding for today, the greater the probability that molecules will collide with sufficient energy and proper orientation, the higher the rate of the reaction. We're going to talk a lot about this energy and this orientation in a little bit. All of what we are studying is called kinetics. This is just the rates of chemical reactions. So kinetic molecular theory of gases, sometimes we refer to it as KMT because it's a lot easier to say, is based on the following assumptions. These assumptions are not completely accurate, but if we tried to be really accurate, the math would be crazy sauce. So we know that gases consist of large numbers of particles moving at crazy high velocities and in random directions. For us and our mathematical calculations, we're going to assume that the size and the mass of gas particles are negligible. We know that gas particles do have sizes, they have volumes, they have masses, but we're going to work on the assumptions that they're so small they don't matter. In reality, they matter, but we're going to pretend like they don't. We're also going to assume that collisions between particles are elastic. What that means is that if I have two gas particles that run into each other, they collide and then bounce off of each other, we're going to assume that all of the energy that those particles had when they came into the collision is conserved. Everything that they have coming in, that energy is all conserved in the particles going out. In reality, the interactions, the friction, the heat loss due to the collision are going to change the quantity of energy that's in the particles. But again, for us, we're going to pretend like collisions are completely elastic. And this one is super important to remember. The average kinetic energy, remember that kinetic energy is the energy of moving. Average kinetic energy of all the particles in a sample is proportional to the absolute temperature of the sample. So in chemistry, when we're talking about temperatures of samples, we're thinking about how fast are they moving. The faster they're moving, the higher the temperature. Good? All right. So let's talk about collision theory. In order for a chemical reaction to occur, three things have to happen. And these are our postulates of collision theory. Particles have to collide. If our molecules don't run into each other, there's no way that they can react with each other. So particles have to collide. Those collisions have to be in the correct orientations. And so if they aren't facing toward each other the correct way, then a reaction isn't going to happen. So we have to have the correct orientation, that correct facing of the molecules. They need to run into each other in the right directions. And then we also have to have enough energy. We kind of call this activation energy. They have to have at least the quantity of activation energy when they collide in order for a reaction to occur. Let's look at what that means on our potential energy diagram. This is the energy of our reactants in the potential energy diagram. We need to have enough energy to get all the way up here, activation energy. That collision needs to include sufficient energy to get all the way up here to this activated complex, which is where all of those molecules have kind of popped apart. We've broken all the bonds of the reactants. That's the activated complex. When we form the new bonds in the products, of course, we're going to release some energy because the products are going to be more stable than this activated complex. And so we're going to have a reduction in energy going from the activated product complex down to the products. Since we do have more energy in the products than in the reactants, this is a positive delta H. This is an endothermic reaction. Catalysts are super cool. They're substances that decrease activation energy, but they're not going to be consumed in the reaction. So whatever the catalyst is, we will have it at the end of the reaction. We can use it in another reaction, which makes them super handy in industry and in our bodies. In our bodies, catalysts are enzymes. So all of our enzymes are catalysts. How a catalyst works is this. It's going to decrease that activation energy. So let's say I'm looking at this reaction. I'm going to take this ethane molecule. Notice that double bond between my two carbons. I'm going to hydrogenate it. I'm going to add this hydrogen addition reaction to make, looks like I've got some ethane down here. So here is the energy of my reactants, the hydrogen and the ethene. Without a catalyst, I need to add this much energy to get to that transition state. Sometimes we call that the activated complex. So that's my activation energy. This is the amount of energy that I need to add to break all the bonds and the reactants so that I can make those products. If I add a catalyst, notice that I only have to add this much energy instead. This is my activation energy of the catalyzed reaction. The catalyst is going to reduce the activation energy. I need this much energy to break the bonds. Without the catalyst, I only need this much energy to break the bonds with the catalyst. The catalyst basically just puts a little bit of a strain on the chemical bonds, makes it easier, less energy required to break those chemical bonds. Notice that when we form the new bonds, we end up at the same place with our products, regardless of whether we had or didn't have that catalyst. And so our total delta H will not be changed. So our products, our reactants, that difference remains the same. This happens to be an exothermic reaction because our delta H is negative. Delta H does not change with the catalyst. The only thing that changes is that quantity of activation energy. Good? All right. We can describe our catalysts as being homogeneous or heterogeneous. Remember that homo means same, so homogeneous catalysts are going to be in the same state of matter, the same phase as the reactants. If I'm looking at chlorine and ozone depletion, because these are all gases, all of these are gases, this would be considered a homogeneous catalyst. Heterogeneous catalysts are not in the same phase. Our catalytic converters in our cars, the catalyst, the metals in the catalytic converter are solids, and they're acting on gases. And so heterogeneous because they are not in the same state of matter. Lots of different factors will affect the rate of reaction. Catalysts definitely can speed up reactions by decreasing the activation energy. Temperature, if we increase the temperature, that means that our molecules are moving faster. Faster moving molecules means that they're going to run into each other more often. We're going to have more collisions, and those collisions are also going to be more energetic. And remember that our postulates of collision theory state that we need to have collisions, and we need to have collisions with sufficient energy in order to overcome activation energy. Increase in temperature is going to increase the collisions and make those collisions more energetic. Concentration of reactants also is going to result in more collisions. More collisions means more reactions, faster rate. Also, particle size of the reactants in solid phase. So if I'm looking at a bunch of little pieces of salt versus a giant crystal of salt, because I can act on these salt molecules on all of these surfaces, increase surface area, with the smaller reactant pieces, we're going to increase the rate of reaction. If I have a giant chunk of stuff, I can really only act on the outside surface. Only that outside surface is going to have collisions. And so the smaller the particle, the faster the rate of the reaction. We can describe the rate of reaction by looking at the change. Remember that delta means change, the change in concentrations of reactants or products over the change in time. Our units, these ones are looking at concentration. So here's concentration molarity, moles per cubic decimeter. And then we could do per seconds, we could do per minutes, we could even do per hours or days if we're looking at really, really slow reactions. But most of the time, we're probably going to be in minutes or seconds. Ways that we can measure changes in concentration. I could look at pH if I have acids and bases, or I'm producing acids and bases. We could look at conductivity if I have ions, different numbers of ions in the reactants and the products. If I have a solid that's being consumed or a solid that's being produced, we could look at changes in mass. If we are producing a gas, we could collect the volume of that gas. We could also look at color changes, especially if we have reactants and products that have different colors, or if we're using an acid-base indicator. This lovely graph is showing us our reactants here turning into our products here. Whoa, that was a weird arrow. I'm not sure what happened there. Notice that we start with lots of reactants. We start with lots of reactants, and over time, the reactants are turning into products. We don't start with many products. Over time, the reactions are turning into products, and so we have an increase in the number of product molecules. This reaction goes pretty much to completion. Notice that the number of reactant molecules is very, very small at the end of this graph. And so this guy at equilibrium definitely favors that forward reaction very, very strongly. So I mentioned that we could look at that rate of reaction by looking at the change in concentration over the change in time. We can look at change in concentration of either the reactants or the products. I can also look at volumes over time. Average rate is going to be from the very beginning of the reaction to the very end of the reaction. So here I could look at the production of products, and I would start at this point and I would finish at the end. And we could either do some calculations, delta y over delta x. I could draw a line, pretend like that's a straight line. I could draw a straight line from the origin to the end of our reaction and then calculate slope of that line. And so delta y is going to be, looks like 50, delta x is going to be 60, and so this would be a positive rate of reaction because I'm increasing the amount of product. I could do the same thing with my reactant, and I would have the same number, but it would be a decrease, a negative slope instead. Let's say that instead of average rate, I wanted to find instantaneous rate, literally the rate at some instant in the middle of the reaction. So what I could do is some big math and find the limit as the change in time approaches zero, looking at that change in concentration over the change in time. Or we could go way easier and instead find that point. Let's say that I wanted to look at the instantaneous rate at time equals 20 seconds. I'm just going to draw myself a nice tangent right there. And then I'm going to calculate the slope of that tangent line. That's going to be my instantaneous rate. Initial rate is similar to instantaneous rate. It's just instantaneous rate at time equals zero. So at the very beginning of the reaction, what is that initial rate? We could again do the limit, but way easier, draw a tangent. So we can draw a tangent right there at time equals zero. Oh, that's really bad. Pretend like that's a line, that's a tangent. And then we could calculate the slope of that line, and that would be our initial rate, which is instantaneous rate at time equals zero. Rate equations look super complex, but it's really everything that we've been talking about just mashed up into one giant line of things. So reaction rate, we talked about before, is that change in the concentration of the reactions or the products over the change in time. Rate is always going to be over a change in time. If I have an equation that looks like this, where I've got these reactants with these coefficients, these products with these coefficients, then I can do a negative change in the reactions over time, the reactants over time, because they're being consumed, I'm using them up, and so their concentrations are going to go down. To accommodate for the coefficients, we are just going to divide by those. So it's kind of like mole ratios in stoichiometry. We're just going to divide by the coefficients. Negative, if it is a reactant that's being consumed, the concentrations should be going down. If it is a product that we're producing, then the concentrations are going to go up, and we're going to keep that positive there. Good? All right. So let's look at this one. Which experiment shows the fastest rate of reaction, A or B? And this question is terrible because it's not specific enough. If it was asking me for fastest initial rate of reaction, then we could definitely say A, because the slope of the lines at time equals zero, A is definitely going to have a steeper slope. It has a faster initial rate of reaction. But if I wanted to do average rate, they're the same, my friends. Ooh, that was a good line. I'm so proud of myself for that one. That average rate's going to be the same, beginning of the reaction to the end of the reaction. They kind of end up in the same spot. If I wanted to look at maybe this point in time, I'm going to say that my B slope might be a little bit steeper than my A slope. So which one shows the fastest reaction rate? It depends on what kind of rate we're looking for. Here's another nice practice problem looking at magnesium and sulfuric acid. Deduce the rate equation. The rate equation is just that ratio of the change in the concentrations of one of our reactants or products over the change in time. So that's the same thing that we've been talking about. Rate equation, just looking at our graph that's given to us, we probably want to put the change in hydrogen gas over the change in time. And since this is one of our products, we're going to make it positive. So this would be our rate equation. The average rate, so we're going to go from the very beginning to the very end of the reaction. So looks like that's, I'm going to say like 3.5 minutes. I know that's not super specific. You should be more specific. So our change in hydrogen gas volume over our change in time is going to give us our average rate. Good. Instantaneous rate at time equals 1 minute. Again, we're going to find that point, and then we're going to draw ourselves a nice tangent. On the test, you'll have a ruler, so you can draw a much better tangent than I just did. And then we'll just count our delta y over delta x to find the slope of that line, and that'll be our instantaneous rate. Easy peasy. We're going to wrap back around to the beginning of this lesson and review collision theory and kinetic molecular theory of gases, just so that they're super fresh in our mind as we go into our last little idea for this lesson, which is Maxwell-Boltzmann distribution curves. So just remember that collision theory, the greater the probability that molecules will collide with sufficient energy, that's sufficient energy to overcome activation energy, and proper orientation, the higher the rate of reaction. So we're focused on this energy and orientation. And then remember that kinetic molecular theory, we're looking at these particles that are moving at high velocities. They are colliding. We're assuming that those collisions are elastic. And then this is the big important piece for Maxwell-Boltzmann. The average kinetic energy of all the particles in a sample is proportional to the absolute temperature of the sample. So let's look at this whole idea of kinetic energy in a sample. Maxwell-Boltzmann curves, energy distributions, are going to graph the numbers of particles, or we could do like the percentages of the particles over energy. And this is kinetic energy. So kinetic energy, the energy of moving. So in a sample, we're not going to have all of the particles have the same exact temperature, but instead we'll have a couple little particles. This is the frequency or the percent of the particles that have this amount of energy. We'll have some things that are moving super slow. We'll have lots of things that are moving an average amount, and that's going to give us our temperature. So temperature, absolute temperature in Kelvin, is the average, is proportional to the average, the kinetic energy of all of the particles in this whole entire sample. So all of these gas molecules in this curve, some are moving very slowly, and then these guys are moving super fast. So these little pieces, let me find a color that you can see. These little pieces over here are moving super, super fast. Because activation energy is here, so on my x-axis I have energy, kinetic energy. This is the kinetic energy equal to activation energy. So the only molecules that can actually react in my sample are these guys. These are the only particles that have more than the activation energy. These are the only ones that are going to be able to overcome the activation energy when they collide. Good. All of these guys are just going to be floating around doing not a whole lot. They might run into each other here and there, but not with enough energy in order for a reaction to occur. So making sure that we remember what those axes are. So label both of the axes. Remember that our y-axis is going to be either the number of particles or the frequency of the particles. We could have the percentages of the particles that are in different amounts of kinetic energy. So these are our kinetic energies. Good. So it's also asking us to explain by annotating the graph how catalysts increase the rate of reaction. I'm going to go ahead and add a line here for my activation energy. So EA is activation energy. That means that these particles are the only ones that have sufficient energy in order for a reaction to occur when they collide. If I add a catalyst, remember that catalysts decrease the activation energy. If this line right here is my regular activation energy with a catalyst is going to be lower, less, more to the left. So maybe this is my activation energy with a catalyst. The first guy was without a catalyst. Notice that we now have more particles that have sufficient energy for the overcoming of activation energy. We have more particles that can collide with sufficient energy in order for a reaction to occur, and that is how we increase the rate of reaction by adding a catalyst according to this Maxwell-Boltzmann energy distribution curve. So, quirky thing here about temperature and Maxwell-Boltzmann. As the temperature increases, so does the average kinetic energy of the particles, right? So if my average temperature, or if my average kinetic energy here relates to 0 degrees Celsius, if I increase the temperature, now my average is 25. Now my average kinetic energy is proportional to 100 degrees Celsius. Notice that the peak of our curves does shift to the right, but it also flattens down the curve. So our curve gets a little bit more flattened, it's more spread out. So instead of having a nice normal-ish distribution curve, it's going to be a little bit flatter, and the peak is going to be a little bit more to the right. So flatter and more to the right. Adding that temperature is going to also increase the number of particles that have sufficient energy to overcome activation energy. So this little divot right here is for that coldest temperature. If I increase the temperature a little bit, notice that I have more particles under the curve. If I increase even more the temperature, oops, I definitely traced the wrong line there. If I increase even more the temperature, I have even more particles that have enough energy to overcome activation energy. So this question is asking us to sketch two Maxwell-Boltzmann curves on this graph, on this axis. One that has a temperature of T and another one has a T prime temperature that is higher than T. Label both axes. Remember that our y-axis is going to be the number of particles or the frequency of particles or the percentage of particles. And then our x-axis is energy or kinetic energy. We're going to start our temperature T curve, so our lower temperature, and it's going to be a normal-ish distribution curve, but with a little bit of a tail. That's probably not the best one, but we'll go with it. At a higher temperature T, what's going to happen is our curve will flatten out a little bit and it's going to peak a little bit more to the right. Good. When I add in my activation energy, maybe this is our activation energy, notice that these are the only particles that have sufficient energy to overcome activation energy, whereas at my higher temperature, we have way more particles that have energy sufficient to overcome activation energy and react. Good? Good. Before we put this day away, super quick look at these two kinds of graphs. Make sure that you do not confuse them or merge them into a single graph. This guy here is Maxwell-Boltzmann distribution curves. It is literally the distribution of the kinetic energies of the particles in a sample. The average kinetic energy is proportional to the temperature, right? Notice that I've got energy here on the x-axis, and it is specifically kinetic energy, that energy of movement. This other graph also has energy, but it is potential energy, not kinetic energy. We call this a potential energy profile, or we could call it the reaction coordinate. This guy is showing us the energy that is bound up, the potential energy that is bound up in the chemical bonds of the reactants and also of the products. We can see the activation energy is here. How much energy do I need to add to the system in order to break the bonds in the reactants? how much energy is released when we form the bonds in the products, we can look at that activation energy. Is that difference from reactants to that activated complex? We could definitely also add a catalyst and see that we could lower the activation energy. Potential energy here on the y-axis. In our Maxwell-Boltzmann curve, we have kinetic energy on the x, not the y. Here we have that number of particles, or we could have the percentage of particles or the frequency of particles would all work. This guy is showing us activation energy here. If I wanted to add a catalyst, I would lower activation energy. So notice it's not going this way, but instead it's going this way. These are all the particles that would have sufficient energy to overcome activation energy and react without a catalyst, and these are all the guys that could react with a catalyst. We did it. Objectives accomplished. We described collision theory and kinetic molecular theory of gases. Postulates of collision theory. In order for reactions to occur, three things need to happen. There needs to be a collision between the reactant molecules. That collision needs to have sufficient energy to overcome activation energy, and those collisions need to be in the correct orientation for those bonds to be broken. We talked about catalysts. Catalysts reduce activation energy, which allows for faster rates of reaction. We talked about how catalysts and some other things, temperature, concentrations, particle sizes, surface areas, can affect rates of reaction. We talked about how we can measure rates of reaction. We can look at changes in volume, concentration, pH, color changes. We talked about calculating rates of reaction. The easiest thing to do is to draw a tangent and find the slope. And then we looked at Maxwell-Boltzmann, and we're going to make sure that that is not the same thing as a potential energy diagram. Good work today.